Illustration of Floyd Warshall algorithm. In the last lecture, we learned about Floyd Warshall algorithm. Here we are going to see how you can apply this algorithm on a graph in order to find shortest path between all pairs of vertices. This is what we are going to do. What we'll do is, we'll take a small graph and construct the whole distance matrix. Then we'll see how the updations are to be done in the distance matrix. Okay. We are taking a smaller graph because otherwise it will be very lengthy, because each iteration you have to update this complete distance matrix. In case of Bellman Ford, we just have to update one distance array, a one-dimensional array. But here is a complete matrix, two-dimensional matrix. So what we'll do is we'll take a smaller graph. Let us take a graph like this with 4 vertices. This will be good for our purpose. We'll say the vertices are A, B, C and D. These are the vertices. I'll have one edge from A to B, one from, let us say, C to D, one from B to C, B to D and A to C. Let this be the graph. Okay. In this graph, I'll give some weights. A, B, let it be 1. Then I'll say BC is 2, AC is 4, BD let it be 5 and CD will be 1. Here I'm keeping all the edges as undirected edges. You can use directed graphs as well. For all those, Floyd Warshall algorithm will work perfectly. Here I'm using undirected. Okay. First thing is, we have to construct the distance matrix. What will be the size of my distance matrix? We learned that distance matrix should be of size V cross V. Here V is 4 because I am having 4 vertices in the graph. So V cross V will be 4 by 4 matrix. This will be my 4 by 4 matrix. Okay. 1, 2, 3, 4. This is the matrix that I am going to update. What I'll do is, instead of putting numbers, I'll just name it as the name of vertices so that it will be easier for you to understand. You'll easily connect what vertex I'm talking about. So from here, you can directly see that this particular block will correspond to distance from A to A. This is for distance from A to B. This is for distance from A to C and so on, right? So for all pairs of vertices, I'm having one entry in this matrix. What is the initialization to be done? We learned that while initializing, all the distances from a vertex to the same vertex, dii, this will be equal to 0, which means A to A is 0, B to B is 0, C to C is 0, D to D is 0. This is the initialization. Then, if there is an edge wij between any particular set of vertices I and j, then the entry will be this weight wij. So for all those vertices which are having weight, we'll put wij. If there is no weight, that is, if there is no direct edge from that between those two vertices, then we'll put distance as infinity. Okay. So what about AB? AB is of distance 1. So we'll put 1 here. AC is of distance 4. So I'll put 4 here. AD, there is no direct edge, so I'll put infinity here. BA and AB are same. So what I'll do is this row I'll copy into this column because AB and BA are same. Similarly, AC and CA are same because this is undirected. So I purposefully took an undirected graph so that entries will be easier. Otherwise, for all these entries also will again consume time. Here the purpose is to make you understand the concept. So we'll go through the whole algorithm. Okay. What about BC, this entry? BC is having edge weight 2, BD is having edge weight 5, which means here it will be 2, here it will be 5. CD is having edge weight of 1, so this will also be 1. This is the distance matrix we are having. What do we have to do now? We have to take each vertex as intermediate vertex and then we have to update this distance matrix. This is the task. So let us start with A. We'll take A as the intermediate vertex. My intermediate vertex is A now. Okay. Considering A as intermediate vertex, let us update all the entries that are present here. Okay. One thing I'll do is, any distance from A to any other vertex, be it B, C or D, these are not going to change if I have A as intermediate vertex. The reason is, how will I update the distance A to, let us say, AB? This should be updated as, while considering A as intermediate vertex, it will be AA plus AB. But AA will anyway be 0, so it will remain as whatever was previously there. So it doesn't make any sense here for us to again consider and update values from A. Ideally, in your algorithm, you should do, but here I am skipping this part. Okay. So this row and this column, both of these I'm skipping because there will be no change in values. We already know that because A is the intermediate vertex we are considering. So let us consider other values. What about this column BB? Will there be any change for BB? Let us see. For BB, initially it was 0. If we consider A, then it will be BA plus AB. What will be the value here? BA and AB both are 1. So it will be 1 plus 1 is equal to 2. But 2 is larger than the existing value. So we don't have to update. Whatever is existing, 0. This is the better value, right? Next, let us consider this one, BC. If you consider BC, what happens if you consider BC? It will be BA plus AC. One more thing, when I am taking these values, ideally I should not directly take it from the graph. I should see this matrix. In this matrix, whatever are the values, that is what I want to pick. So in this matrix, if I say BA, which corresponds to this particular block, okay, value is 1. So BA will be 1 plus what about AC? AC is this one, 4, okay. So if I take AC, then it will be 4. So this will give me 5. My new value for BC is 5, but the existing value for BC is 2, which is better. So I'll keep the existing value, which is 2. What about BD? For BD, if I go through A, for BD, it will be BA plus AD. If I do this, BA's value, from here it is 1, BA is 1, plus what is the value of AD? AD is infinity here, right? AD's value is infinity. So 1 plus infinity will give me a total of infinity only. So 5 is better than infinity, and because of which I will keep 5 as it is, right? What about next one? Let us say I'm considering this particular row. CA I can skip. Next is CB. CB is presently 2. If I take CB with A as intermediate vertex, what will be the value? It will be CA plus AB. Presently CB is 2. If I take CA itself is 4. 4 plus AB is 1. So it will be 5. But 2 is better than 5. So I'll keep 2 here. Okay. 2 will be kept as it is. This 4 is also kept as it is. This 1 is also kept as it is. What about next one? CC I'm not updating because it will be 0 only. It's the same point. CD is already 1. Again, I'm not updating because going to CA will again increase it from 1. Okay. So in order to not take up your time, I'm not updating that. Next is this one, DB. It is 5. Let us check it out. If you take DB, DA I'm not considering because it will be DA plus AA. DB, this will be DA plus AB. If you see this, DA is infinity. Because DA is infinity, total answer is going to be infinity. 5 is better than infinity. I'm not changing it. What about DC? This one, if you take DC, it will be DA plus AC. Value of DA from here is infinity. So again, it will go to infinity. 1 is way better than infinity. We'll keep 1. 0 is also the best possibility. We don't have negative weight edges here. I'm not changing it. So when you considered A as intermediate vertex, nothing changed. The whole distance matrix stayed as it is. Not a single value changed. Can you stop the algorithm here like you did in Bellman-Ford? The answer is no, you cannot. In case of Bellman-Ford, you stopped because though you were relaxing all the edges. So in one iteration, after relaxing all the edges, if nothing changed, that means nothing is going to change if you run any more number of iterations. But in this case, you were considering A as an intermediate vertex. Next iteration, you are going to consider B as intermediate vertex, and now things can change. That is why you cannot stop, but you have to go through the whole process. You have to take each as intermediate and see. Okay. Let us take B as intermediate vertex. So considering B as intermediate vertex, I will skip this row and this column because both of them are having B as one end. So there will be no change in these two. Let us consider all other ones. AA, because it is 0, I am skipping. What about this one? AC, this particular value, which is presently 4. If you take AC, that is equal to, considering B as intermediate, it will be AB plus BC. What is the value of AB here? AB is 1, AB is 1, plus BC is 2. BC is 2, which means total is 3. My present value of AC is 4 and 3 is a better value than 4. See, this is where you can do an updation. Here 3 that we found by taking B as intermediate vertex is a better value than the existing path from A to C. If you see in the graph, this is 4 that was previously existing from A to C. When you took B as intermediate vertex, what happened? You came from A to B and then B to C. This is having a total cost of 1 plus 2, 3, which is smaller than 4. That is why we are updating. Okay. I'm just trying to relate what we are doing with what is there in graph. I want you to understand that whatever change we are doing in this matrix, that is in accordance with what is present in the graph, right? So I'll be changing this value to 3. This will remain as 1. This will remain as 2. So I'll just circle this value so that we'll understand we changed it in this iteration, just to see what changes we made in this iteration. Okay. Next one is this one, AD. If you take, okay, AD, this one. Okay. When you take AD, what happens? Let us see. AD is equal to B is the intermediate vertex. So it will be AB plus BD. What happens here? AB value is 1 plus BD. BD value is 5, which means you will get a total of 6. The value 6 is much lesser than infinity, which means you have to substitute this infinity with 6. Okay. So this is the second change we are making in this iteration. This will remain as 5. This will remain as 1. Next one, let us take this one, CA. If you take CA, that will be CB plus BA. That is equal to, what is CB? CB is 2 plus BA is 1. BA is 1, it will give you 3. So the new value here, it was 4, we are updating it to 3. So this will be updated to 3. This will stay as 2. This will stay as 1. So these are the updations we are doing in this iteration. So DA, I'll directly update it to 6 because see, this column and this row, this will have the same values because it is an undirected graph. So in order to reduce computation, I am directly putting this value here. Next one is, you considered CA. CB you don't have to consider because B is the intermediate. Then see, ideally in algorithm, you have to consider everything. Here I am skipping. So CC, it is already 0. So I am skipping. CD, it is 1. So 1 cannot be improved here because all edges are at least 1. So I am skipping that as well. Let us take DA is already done. DB is done. DC is done. DD is done. So we'll skip all those in this particular iteration. What you can see here is, in this iteration, you were able to change 4 values in your distance matrix. Your AC, CD, CA and CD. You got 4 new values. This is how the updations are happening. Let us go to the next iteration. In the next iteration, your intermediate vertex will be C. C is your intermediate vertex. Let us see if by considering C, there will be any improvements. I'll revert this to 3, 6. I'm just removing the circle. Okay. 3 and 6. Considering C as intermediate, I will skip this row and this column because those are having C at one edge. Considering all other values. First one in this row, AA I am skipping because it is having value 0. AB also I'm skipping because it is 1. You can't improve better than 1 because all edges are at least 1 here. AC we can skip because C is at 1 edge. AD, let us see this. 6 is the present value. If you take AD, see, ideally you should not skip anything. Here I'm just skipping because it's visibly skippable and we have to, we should not drag this lecture very long, right? So this will be AC plus CD. I just want to show you where the changes are happening, okay? AC is 3 plus what about CD? CD is 1. So this will give you total of 4. What is the existing value at AD? It is 6. So your value 4 is smaller than 6, which means you can substitute this 6 with 4. So this is one change that we made in this iteration. This 3 will remain as it is. This 1 will also remain as it is. Next value to be taken. Let us take this row. In that BA is 1, I am skipping. BB is 0. BC is 2, but C is at 1 end, so I am skipping. Let us take BD, the last value here. If you take BD, what happens? BD equal to C is our intermediate. It will be BC plus CD. What is BC? BC is 2 plus what is CD here? CD is 1. 2 plus 1 will be 3. What is the existing value of BD? It is 5. Because it is 5, you can change it to 3. This is the next change we made in this iteration. Okay. So you can see how a Floyd Warshall algorithm is improving, right? Next thing, this row you can again ignore because C is at one end. Then these two values, DA and DB, these two I am directly going to update because it will be same values here because it is AD and BD. It is same. These two are same as DA and DB. Okay. It is undirected graph. So I am directly putting the values 4 and 3 here. What you have to see here is at the end of this iteration, considering intermediate vertex C, we have 4 more changes in our distance matrix. What are the changes? One is in AD, one is in BD, one is in DA, and the other one is in DB. You got 4 edges change. That is distance between 4 pair of vertices change, not 4 edges, distance between those pair of vertices. Okay. So we'll go to the last iteration in which we'll be considering D as the intermediate vertex. I'll remove these circles here. 4, 3, 4, 3. Okay, D is the intermediate vertex, which means I'll be skipping this row and this row. Again, this skipping you actually don't need to do. Here I'm skipping because you know D is one end. D is at one end, so there is no point in using D as intermediate vertex. We'll take all other values. We'll take the first row. AA, it is already 0. We'll skip. AB is 1, which is smallest possible value. We'll take AC. Okay. If you consider AC, it will be AD plus DC. What happens here? AD is 4. AD is 4 plus DC is 1. This will give a total of 5. But the existing value of AC is 3, which is better than 5. What should you do? You should make no changes. You should keep 3 as it is. 3 should be kept as it is. And you should not update. 4 and this 1 will be kept as it is. So this is it about AD. AC. Then it is AD. D, this row, we are this column we are skipping. So I'll skip D. We'll go to the next row. B's row. BA, BB are already smallest possible values. BC. Let us take BC. BC equal to BD plus DC. That is equal to what is BD? BD is 3 plus DC is 1. So it will give you a total of 4. 4 is larger than what is already there at BC. The BC is presently 2. So you should not update it with 4. You should keep it as 2. This should be kept as 2. This should be 3 only. This should be 1 only. BC is also done. Next, we will go to the next row. BD I am not considering because D is an intermediate vertex. It will be BD plus DD. DD will be 0. So we'll skip. Next row, there is CA. Let us take CA. CA is equal to CD plus DA. Considering DA as intermediate. CD value is 1 plus DA value is 4. This will give you a total of 5, but the existing value of CA is 3. So you should not make the change. You should keep this 3 as it is. Okay, this 4 will also remain. This 1 will also remain. Next is CB. If you consider CB, what happens? CB is equal to CD plus DB. If you consider this, CD is 1 plus DB is 3, which will give you a total of 4, but the existing value of CB is 2. 2 is better than 4, so you should keep 2 as it is. This will be 1 only, this will be 3 only. Okay. Next one, so this row is also done. We'll go to the last row, which is D only. So I'm not considering last row because see, you take anything starting with D, DA, DB something. Then if you take D as intermediate, it will be DD plus DA. DD, you know, it is anyway 0. So there is no point in doing this computation. So we are done here. Okay. We are done with all the pair of vertices and we considered each single vertex as intermediate vertex and updated all the values. That is for all the pair of vertices possible, we have done the updation. This is the final distance matrix you are having. This tells you the shortest possible distance between every single pair of vertices that are present in this graph. This is the final output of Floyd Warshall algorithm. Okay, you found out what are the shortest possible distances between every possible pair of vertices, right? So this is the final distance matrix with Floyd Warshall algorithm. So I wanted you to be clear on how you can apply this algorithm on a graph. See, whenever you are learning an algorithm, it is important that you understand the algorithm, understand the logic. You also understand how you can actually apply it. In real life, when you're given it to apply, you should be able to apply. So that is what I want you to know. In the next lecture, we'll see how you can write code for this. These are the 3 things you should know. 1, you should know the algorithm. Then you should know how you can apply this algorithm, how it actually goes through. And then you should know how you can convert it into code. If you know all these 3 things, then you are perfect with this algorithm. Okay. So in the next lecture, we'll see how to convert this algorithm into code.